Before I get started, I should probably warn you that in this video, I go through some pretty high-level physics and I go through it really fast. I basically go through the physics as if you were students in an advanced physics course on electricity and magnetism at an elite university. I'm not saying that to discourage anyone from watching this video, only to warn you so you don't get overwhelmed. What I advise if you want to watch this video, and I do hope you want to watch this video, is to watch the video just to get an overview of what I am saying without checking the validity of every statement. Then go back and check on individual things that you want to examine further. Now back to the video. John Henry Poynting was inspired to create the Poynting Vector because of James Clerk Maxwell's work over 3 long papers and a textbook on what is known as Maxwell's equations, or at the time, the Maxwell-Faraday equations, as Maxwell's equations were inspired by the theories of Faraday. In the Maxwell-Faraday equations, Maxwell created 2 types of magnetic fields, a magnetic induction B and a magnetic intensity or magnetic force H, which are related to each other in a uniform medium by a magnetic coefficient called the permeability mu, or B equals mu H. However, it wasn't particularly clear from Maxwell's papers which magnetic field, B or H, was the main magnetic field parallel to the E field. For example, in Maxwell's famous 1864 paper, Maxwell represented light as following a wave equation of the magnetic induction B, implying that light is an EB wave, or maybe just a B wave, and that B was the main magnetic field. Then, in 1873, Maxwell seemed to have changed his mind when he wrote in his textbook that linearly polarized light was composed of vibrating electromotive force E and a perpendicular magnetic force H. However, in his diagram, Maxwell labeled the vibrations as electric displacement versus magnetic force. And as the electric displacement is given the letter D, it is not clear what Maxwell wanted. Tragically, Maxwell died in 1879 before he could clarify his theories more. Anyway, Maxwell's 1873 book inspired Poynting, who was a former student of Maxwell's, to publish a paper in early 1884 on the transfer of energy in the electromagnetic field. In that paper, Poynting stated that there was a power density depends on the electric intensity E times the magnetic intensity H times the sign of the angle between them, or in modern vector math, S equals E cross H. This was immediately appealing to scientists, as it seemed to settle the debate about what kind of vibrations were involved in light, towards light being a vibrating EH wave. Poynting's viewpoint was also amplified when, in 1900, Poynting and his good friend J.J. Thomson, who had used Maxwell's equations to discover the electron a few years earlier, co-wrote a very popular undergraduate textbook on physics, the first volume of which was still being used with undergraduates in 1947. Fast forward 1 year to 1948. That was when the physicist Arnold Sommerfeld became the first physicist that I know of to insist that B is the main magnetic field parallel to the electric field E. However, despite that, Sommerfeld still believed in the Poynting vector and that light is a vibrating EH wave. On a side note, the delightful engineer Charles Proteus Steinmetz seemed to have used B as the main magnetic field, as well as championed the term magnetic field over magnetic lines of force as early as 1897, but he was ignored by most physicists. Anyway, Sommerfeld's book was translated into English in 1952, a few months after his death, and it ignited a big debate about the nature of the magnetic field that was still raging in 1961 to 63. That was when a 43-year-old charismatic physics teacher at Caltech, on the cusp of winning a Nobel Prize named Richard Feynman, taught a 2-year-long course to undergraduates. These lectures were recorded and made into a wildly popular textbook, which can still be found on the bookshelves of most physicists to this very day. Feynman agreed with Sommerfeld that B and E are physically the fundamental fields, and it was only some confusion in the past which caused people to think that H was the magnetic field. However, unlike Sommerfeld, Feynman believed in both the Poynting vector and that light was an EB wave instead of an EH wave. Feynman created this miracle by writing a new equation for the Poynting vector, something quite new as he put it. Instead of the Poynting vector equaling the E field cross the H field, it was equal to the E field cross the B field times the speed of light in a vacuum squared times the electric coefficient in a vacuum. The strange thing is these equations are equivalent if and only if the material is in a vacuum. Anyway, after the popularity of Feynman's lectures, especially Feynman's insistence on the Poynting vector being strange but true, the Poynting vector gained popularity in textbooks and peer-reviewed papers, although most people wrote it in a simpler form of E cross B over mu naught, which is mathematically equivalent to how Feynman wrote it, i.e. only true in a vacuum. Then, in the late 1990s, a famous scientist, and yes, textbook author, named John Dave Jackson, wrote a series of papers that promoted using a sleeve of surface charges to allow the Poynting vector to point down the wire in a direct current circuit, differing from the DC theory promoted by Poynting, Sommerfeld, and Feynman, where the Poynting vector points into the wire. In the last 5 or 6 years, the Jackson model and the Poynting, Sommerfeld, Feynman model of the Poynting vector in DC systems has become particularly popular among YouTubers looking for unusual physics to discuss. Which brings us to today. But before you spend too much time trying to understand these models, let me just say that trying to use the Poynting vector to explain physical phenomena is, well, not to put too fine a point on it, but it's dumb. It's crazy. It's obviously nuts and screwy and even absurd. Those are not my words. They're Richard Feynman's. Feynman himself admitted, well, as I mentioned, Feynman's lectures were recorded. So listen to Feynman's actual words about the Poynting vector for yourself.
E cross B is the flow rate, according to this crazy theory. But it tells us a curious thing, that when we're charging a condenser, the energy is in the condenser, it's not coming down the wires, it's coming in through the surface. Screwy. Intuitively screwy. Although it is odd intuitively, the energy is flowing into the condenser from the sides. But to continue to convince you that this theory is obviously nuts, I take one more example, but this dumb thing says that there's a flow of energy because there is an E cross B.
Even when he had time to reflect on his words, as in his famous textbook, he wrote explicitly how absurd it gets. But why? Why would Richard Feynman call the Poynting vector all those names? And if the Poynting vector is illogical, why do we use it? Well, that's why I'm making this video. In it, I will discuss the misunderstandings in John Poynting's derivation of the Poynting vector, then Arnold Sommerfeld's derivation of the Poynting vector and the Poynting theorem, and then finally problems in Richard Feynman's derivations. Ready? Let's go.
Electricity, 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 electricity.
Hello, my name is Kathy Joseph, and yes, I love physics. I use the history of the development of science to teach and understand it on a deeper level. I've come to believe that physics is not in the equations and concepts, but in how we got the equations and concepts from my studies. I have found that occasionally there is a false theory that is believed and used for many years by almost all physicists before someone, usually someone outside of academia, points out the fallacy. For example, in 1777, the great chemist Lavoisier postulated that heat is an indestructible fluid. And over the years, this caloric theory was used to explain chemical and thermodynamic systems like Carnot's theories. Decades after the experiments of Count Rumford seemed to demonstrate that this was false. Then in the 1840s, a beer brewer named James Prescott Joule started giving relentless talks about his theory that heat was really just a form of energy that could be generated with friction. Eventually, this was mentioned in a paper by an Irish scientist named William Thomson, and then used by a German scientist named Clausius to create the first law of thermodynamics. I have a whole video about the history of the first law of thermodynamics if you want more details. Or in another example, in 1902, the physicist Philip Leonard explained away the results of the photoelectric effect as atoms having a fuse, where the energy of the emitted electron was independent of the energy of the light that impinged upon it, which he mentioned in his Nobel Prize acceptance speech in 1906. For many years, this was considered settled science, even though in 1905, a patent clerk third class, had the radical idea of taking Max Planck's quantization of light energy literally instead as a way to explain the photoelectric effect. Eventually, Einstein's theories replaced Leonard's. And in 1921, Einstein won a Nobel Prize for this model. Specifically, I think, as a way to insult Leonard and his lackey Johannes Stark, who by this time were well on their way to becoming anti-science Nazis. Once again, I have a video on the history and physics of the photoelectric effect if you're interested in more details. I'm not saying I think like Einstein. I'm saying there is a history of smart physicists twisting themselves into knots to promote weak models if they came from intelligent scientists that they admire. This is not a conspiracy, merely a side effect of physicists being real human beings. We have this idea that if someone is a brilliant, outside-the-box thinker, like Lavoisier or young Leonard or Einstein or Poynting or Sommerfeld or whoever, that they cannot make a mistake. But logically, of course, that isn't true. Every once in a while, a talented scientist promotes a weak idea together with strong ones, and this weak idea ends up permeating into mainstream science. This is actually a good thing, as all new discoveries are in its way an indictment of old theories. If any scientist was perfect, then scientific development would be over. Anyway, through my studies, I've come to believe that the Poynting vector is a weak model. It is erroneously derived and it doesn't work to explain any physical phenomena. In other words, when it comes to the Poynting vector, I agree with Feynman when he wrote in his textbook, How Absurd It Gets. But unlike Feynman, I'm willing to stand up and say I disagree with a crazy, absurd, and illogical theory that makes no sense to me, even if great physicists have promoted it. Which brings me to Part 1, Misunderstandings in Poynting's Derivation of the Poynting Vector. As I mentioned previously, John Henry Poynting derived his famous equation from the model in mathematics of Maxwell's work from 1873. In this, like Maxwell, Poynting used these hard-to-read, wiggly German letters, an extra 4 pi's, which we now ignore, and a few different letters like the capital letter K for the permittivity rather than the Greek letter epsilon. None of which are really that important. I just wanted to tell you so you would know why Poynting wrote his equations the way he did. Short comment about the 4 pi's and why we now ignore them. According to an Italian scientist named Giovanni Giorgi, Heaviside believed that Maxwell arbitrarily added the unnecessary factor of 4 pi because Maxwell wanted the electric force to be proportional to the charges divided by the distance squared, while rationally it ought to be proportional to the charges divided by 4 pi r squared. So this is inversely proportional not to the distance of the charges, but instead to the area of the sphere surrounding the charge. The reason I mention this letter of Giovanni Giorgi is because in it he mentions to Heaviside his theory of irrational units of electromagnetism, otherwise known as SI units. Someday I will do a whole history of SI units. It's really cool. Back to John Henry Poynting. In Poynting's work, Poynting perpetuated a mistake of Maxwell's. In Maxwell's book, he defined the energy density as 1/2 ED and the magnetic density is 1/8 pi BH. Note that Maxwell was so brilliant, but he was so ahead of his time that basically no one could understand him without literal years of study. Even his close friend and mentor, William Thomson, aka Lord Kelvin, couldn't get far enough to truly proofread his work. So everything is chock full of mistakes. I mean, he wrote the equation for the speed of an electromagnetic wave. V equals the square root of 1/epsilon mu in 3 different ways in 3 different documents, and all of them are incorrect due to those darn 4 pi's. Don't get me wrong, I adore Maxwell, but he will give anyone a headache. Anyway, as B equal mu h, and Maxwell routinely replaced D with a constant times the electric field divided by 4 pi, Poynting and Hertz and others defined the total energy density to be 1/8 pi epsilon E squared plus 1/8 pi mu h squared. Poynting then derived his famous equation by starting with his version of Maxwell's equation for the energy per volume and then taking the time derivative to get the power per volume as 1 over 4 pi epsilon e dE dt plus 1 over 4 pi mu h dH dt. The 4 pi isn't that important, but what is important are the hidden assumptions, that the magnetic permeability mu and the electric permittivity epsilon are not dependent on time, and using d equals epsilon e as if it was universally true. Let me explain. As I said, mu h dH dt only equals the time derivative of the energy density if the magnetic coefficient mu is a constant with respect to time. But as mathematically explained by the delightful Charles Proteus Steinmetz in 1890, the fact that the magnetic field B in a piece of iron takes a certain amount of time to be magnetized, when in a magnetic intensity H, causes heat to be produced in iron in alternating fields. This delay in magnetization is called hysteresis, Greek for lag behind. Note that in this original paper, Steinmetz confusingly labels the energy loss with the letter H. This has nothing to do with the magnetic H field, sorry. Anyway, Steinmetz's work means that not only does the magnetic coefficient mu depend on time, but also that a changing magnetic coefficient has a power dependence. As you might expect, I have a similar problem with epsilon e dE dt equaling the time derivative of the electric energy density 1/2 ED. For one, the electric coefficient epsilon is due to the electric properties of the non-conductor, which Faraday called the dielectric, and is not independent of time. See, when the displacement field from static charges goes through a dielectric, the displacement field pushes the atoms in it to be a bit polarized, with one side more positive and one more negative, which reduces the electric field in the material by a coefficient called the relative electric coefficient, epsilon r, where the total coefficient epsilon equals the relative coefficient times the vacuum coefficient. By the way, the coefficient in a vacuum, epsilon naught, has nothing to do with the electric properties of a vacuum, as a vacuum has nothing in it. It's just there to make the units of displacement, amps per meter squared, match the units of electric fields, newtons per coulomb. It doesn't have any physical significance. It's just like the constant K in Coulomb's law. In fact, the constant epsilon naught is equal to 1 over 4 pi k. I've discovered that Oliver Heaviside agrees with me on this point, as in 1902, when Giovanni Giorgi wrote that the coefficients in a vacuum express a physical truth, Oliver Heaviside wrote in the margins, "No, bad logic." Anyway, the polarization of atoms in a dielectric is not instantaneous, which means that the electric coefficient is a function of time. An example of that is in a microwave oven, where a vibrating electromagnetic wave causes the polarized water atoms in your food to spin, which converts into heat. According to modern textbooks, this dielectric heating can be derived from Maxwell's equations and is a function of the frequency of the electromagnetic wave, the electric field squared, and was called the imaginary part of the relative dielectric constant. But even in ordinary situations, the dielectric constant is a function of the frequency of the light that goes through it, which means the dielectric constant has a time dependence. Finally, object to stating that D is equivalent to epsilon E in all situations. As Maxwell noted in his 1873 book, in conductors, the current density in the wire is equal to the electric field times the conductivity, J equals sigma E, which is called the microscopic Ohm's law. However, if D equals epsilon E, then by simple division, E equals D over epsilon. However, if E equals D over epsilon is the full equation for the electric field everywhere, then E equals D over epsilon is true inside a conductor. That would necessitate that the current density, J equals sigma E, is the same as J equals sigma D over epsilon. Note that the permittivity of a conductor, epsilon, is basically infinite, which means that the current in a conductor has to be zero in all cases, which is, of course, ridiculous. In addition, there is a third equation for the electric field. E equals minus the gradient of phi minus dA dt, which is also equal to the gradient of V minus dA dt, where phi equals negative V is the potential, or the internal energy per charge, and A, called either the magnetic momentum, Maxwell, or the vector potential, Heaviside, is related to the magnetic field B with the function B equals curl A. I like to call the equation E equals grad V minus dA dt the universal electric field equation, as it is universally true, whereas E equals D over epsilon and E equals J over sigma are true only in a dielectric or a conductor respectively, and only true when the magnetic field is constant. I'll explain this in more detail in future videos, but if you want a preview, I recently gave a colloquium at the physics department at UC Irvine on the evolution of Maxwell's equations, and the PowerPoint and my voiceover were recorded, and I put a link in the description of this video. I think from now on I'll just do my physics talks on a whiteboard, as no matter how dynamic I try to make it, I find pure PowerPoint talk static, and I worry it discourages people from asking questions. Anyway, my belief in the universal electric field and the time dependency of the electric and magnetic coefficients is why I do not agree that the time derivative of 1/2 ED plus 1/2 BH is epsilon E dE dt plus mu H dH dt. Instead, it equals the far less elegant 1/2 E dd dt plus 1/2 D dE dt plus 1/2 B dH dt plus 1/2 H dB dt. Whew! However, that was the faulty logic the Poynting used to derive that the energy flows where the amount crossing the unit area per second of this plane is equal to the electromotive intensity times the magnetic intensity times the sine of the included angle, with the direction of flow being in the right-hand order. In other words, Poynting wrote that this energy flow vector equals E cross H because of a faulty derivation of the time derivative of the energy density. This is not an insult to John Henry Poynting or James Clerk Maxwell. Maxwell's 1873 work and Poynting's 1884 work predated Steinmetz's theory from 1890 on changing magnetic permeability due to hysteresis, and far predated equations on dielectric heating, so it makes sense that they would miss it. Heck, their work even predated the creation of the universal electric field equation, E equals gradient V minus dA dt, as Maxwell added another term of V cross B to his universal electric field equation, or E equals V cross B minus dA dt minus the gradient of phi. It was only after Lorentz moved the V cross B to the force equation, F over Q equals E plus V cross B, or F equals QE plus QV cross B, that we ended up with a true equation for the electric field, E equals gradient of V minus dA dt. Note that it wasn't as simple as that, because of course it wasn't. I explained it a bit in my talk at UC Irvine if you want more details. But what about Sommerfeld, who knew most of these things? That brings me to Part 2, Misunderstandings in Sommerfeld's derivation of the Poynting vector. As I said before, Sommerfeld was the first physicist to declare that B, not H, was the main magnetic field. Sommerfeld noted how every equation, aside from the energy, with both magnetic fields and electric fields, either had B's and E's or had H's and D's, concluding with the fact that B and E and H and D belong together follows unambiguously from the theory of relativity, in which the quantities CB and negative IE and H and negative ICD, respectively, are coupled together in a 6-vector antisymmetric tensor. Note that Maxwell's energy equations, 1/2 dE and 1/2 HB, only match electric fields, D and E, or match magnetic fields, H and B. And the power per volume lost in a DC circuit, J dot E, matches the electric current per area, J, and the electric E field. Is only Poynting's vector, S equals E cross H, which matches an electric E field with a magnetic H field. As a side note, Sommerfeld has been called the most underrated physicist of all time, due to the fact that he was so influential and inspirational that he was nominated for a Nobel Prize a jaw-dropping 84 times, more than anyone who didn't win. I have a theory that Sommerfeld didn't win due to being an anti-Nazi German who didn't win before Hitler came to power. I wonder how much a 1937 full-page Nazi article on the dangers of non-Jewish people who had a Jewish spirit affected this, especially as they stated explicitly that the Jewish spirit is probably most clearly recognizable in the field of physics, and then complained bitterly of Sommerfeld's and Max Planck's work in helping their talented students into professorships, even if they were Jewish. But that's just a theory. By the way, in my videos on why Heisenberg volunteered to make a nuclear bomb for Hitler, and on what I think really happened between Heisenberg and Niels Bohr in Copenhagen, I mistakenly said that Nobel Prize winner Johannes Stark wrote that article, but he actually only publicly agreed with it. It came from the top brass instead. Anyway, despite the fact that Sommerfeld believed that B was the magnetic field, he still believed in the Poynting vector, and here's how he derived it. Sommerfeld began with Faraday's law of induction, and then he took the scalar multiplication of H to both sides of the equation. Then he took Ampere's law with Maxwell's addition, and added the scalar multiplication of E to both sides of the equation. Combining equations, he got H dot dB dt plus E dot dd dt plus E dot j equals E dot the curl of H minus H dot the curl of E. Finally, he used the math relationship to get the final equation, that H dot dB dt plus E dot dd dt plus E dot j plus the divergence of E cross H equals 0. By the way, this equation, called the Poynting theorem, is completely legitimate and universally true, which is why it has occasionally been used effectively in physics problems. Then Sommerfeld made the same mistake the Poynting did. Namely, Sommerfeld stated that H times dB dt equals the time derivative of 1/2 hb, ignoring that the permeability can be a function of time, and that d dot dE dt equals the time derivative of 1/2 dE, ignoring that the permittivity can be a function of time, and that d equals epsilon E is only true in a dielectric with a constant magnetic field. In other words, the equation that Sommerfeld derived, known as the Poynting's theorem, while true, does not represent the collective change in energy over time. In fact, I would argue that it is the universal electric field equation that represents the first law of thermodynamics, rather than this meaningless math relation of Sommerfeld's and Poynting's. Please understand, I have nothing but the utmost respect for Professor Sommerfeld. He was a world-class physicist, one of the most inspiring teachers that ever lived, as well as a moral person in a very challenging time. But as with every scientist, great and small, I don't believe anyone is infallible. Also, it would be ironic for me to complain too much about Sommerfeld for making these mistakes, as I made the same mistakes for the vast majority of my career. I mean, just check out this video I made about Maxwell's equations from just 2 years ago. Maxwell stated that if the medium is uniform, then the displacement field D and the electric field E are related by a simple constant K, which Maxwell called the electric elasticity. Years later, Oliver Heaviside decided that he would prefer to use a constant that he called the permittivity that was defined as the inverse of Maxwell's electric elasticity. If we use the Greek letter epsilon for the permittivity, where epsilon is 1 over K, then we get the electric field E is D over epsilon, which makes Gauss's law, the divergence of E equals rho over epsilon. Note that epsilon is a constant that depends on the electric properties of the medium. In the case of a vacuum or air at room temperature and pressure, where there is either no electric properties or limited electric properties, you still need a constant, epsilon naught, called the permittivity of free space, to make the units work out. This situation is so common that often we are given Maxwell's laws for that case as if it was universal. The divergence of E equals rho over epsilon naught. I literally just want to go back in time and yell at myself. No, we can't replace E with D over epsilon as if it was universally true when it isn't true inside a conductor and it isn't true if the magnetic field is changing. And no, we don't replace all our epsilons with epsilon naught because the situation of a vacuum or air at room temperature and pressure is so common that often we are given Maxwell's laws for that case as if it was universal. No, Kathy of 2 years ago, that's not why we write Maxwell's equations with all those epsilon naughts and mu naughts. We write it that way because of how Feynman wrote Maxwell's equations and how he derived the Poynting vector, which brings me to Part 3, Misconceptions in Feynman's Lectures. I would like to start with a bit of my personal history with Feynman's lectures in physics. If you want to skip straight to the physics part of Feynman's lectures, here's the timestamp. When I was a junior at the University of Chicago, called a third year, I was conned by my boyfriend to spend a whopping $120 for the hardback version of Feynman's lectures in physics. Then, considering how much he and others hyped up Feynman's lectures, especially the section on electricity and magnetism, I tried to work through the book. Although I really tried, I could not make heads or tails of it and gave up after a couple of weeks. I'm sure many of you had a similar experience. Luckily, I was in my 4th year of advanced physics work. I had doubled up. And I had an excellent E&M teacher, thanks Herr Mueller, who used a decent textbook, Wagness's Electromagnetic Fields, although I prefer Griffith's. So I knew I could do the material. However, I didn't think to blame Feynman. After all, he was supposed to be the best teacher who had ever lived. Instead, I figured I couldn't learn without a great teacher and gave up on self-improvement through textbooks, which meant that for many years that I was out of school, I didn't learn any new physics. However, I continued to learn through looking through the internet, learning from other people, and obsessively thinking about everything that I love, especially things like music and movies. So many movies. Let me explain. Warning, this is going to get a little bit personal and dark. See, I was born to a family dealing with extreme trauma, as I had a 3-year-old sister who had drowned in a pool the year before I was born. My father was determined to push the family through this tragedy while being a very busy lawyer. So he focused on me to bring the family through, as I was the only non-traumatized person in the family. Now that may sound horrific, but actually I had a lovely and creative childhood. Aside from school that I was mixed on, I loved learning, but I hated busy work and the stifling of originality. Anyway, the main way my dad and I communicated was through movies, and we had a particular fondness for musicals. We would rate them, evaluate them, improve them in our minds, and argue endlessly about them. My dad was an incredibly skilled lawyer and knew the power of truthful storytelling. But he also knew that fiction and humor were usually the best window to learn that art. That is also how I learned that storytelling and kind humor was the best way for me to help my family and friends. Also, my dad would say that a lawyer's only currency is their honesty and would never exaggerate, even in family stories, a practice I follow as well, aside from when I'm having a tiff with my hubby. Because of that, we were always searching for the juiciest true stories and using our skills from examining movies to tell them to the best of our abilities. When I was a kid, I was taken to a science museum called the Exploratorium on a school trip. At the Exploratorium, they have tons of kiosks with different hands-on experiments. I did the do and notice and then read the what is going on section. I immediately thought it was cool and grabbed a friend to show her. That is how I found that teaching physics was so joyful. By the time I got to college, I learned that advanced physics has no busy work and tons of creative debate. So I was in heaven. However, I then found the research part of graduate school to be isolating and pointless and went through 3 different graduate programs before becoming a high school physics teacher. Luckily, I found teaching high school to be amazing. I learned so much from them. My God, you can tell with a room of 34 young teens when they get it and when they don't. And when they get it, you can feel the delight. However, around 8 years ago, after taking a year off from maternity leave, my new principal said that she didn't need me. And if I insisted on returning, I would be forced to teach freshman algebra instead of physics. I know it all worked out for the best, but I'm still mad. Anyway, that is how I decided to take a break from teaching and instead try to write a book about the history of electricity to help non-scientists get an understanding of basic electrical distribution through its history. By the way, my mom came up with the title. Honestly, I only started this channel to get people to buy my book, but then I fell in love with the medium. I can talk about whatever I want for as long as I want to. I can follow any tangent that interests me for as long as it interests me. I really don't understand how more physicists don't want to make YouTube videos. The freedom is fantastic. Plus, putting my material in a visual medium and getting such great pushback and feedback has made me a much better physicist and made my book and later videos much better as well. I think of each video as a mini movie or maybe even a mini musical, with a discovery process like the dialogue and the equations like the songs. By the way, I'm not the only one who sees music in physics. For example, in 1948, Einstein recalled that when he first heard Niels Bohr's model of atoms, he said that it had the highest form of musicality in the sphere of thought. In truth, I see movies and music in everything, not just physics. It's basically become part of how I think. That is why most of my videos are so cinematic. I even made a commercial-free version of this section of the video with even more musical and movie references because I love it so much. In October of 2022, I published my first book, and I have the detailed outline on 5 more. Honestly, my biggest problem now is focusing on 2 or 3 projects when I have dozens I want to develop. One of the surprises of starting a YouTube channel and following those odd tangents is that I learned that with a lot of work and historical context, I could understand the core points and derivations of some of the most notoriously difficult original concepts in physics and engineering. Heck, I could learn and explain subjects like electrical distribution and radio and astronomy, where I've never taken a class. Dankeschön, Herr Müller. Even so, I was terrified to study Maxwell's papers. After all, if Feynman was preferable and I couldn't get through Feynman, what hope did I have to get through Maxwell? Then, around 2 years ago, I had the opportunity to visit the Spark Museum in Washington State, where the owner let me see some original historical papers, most of which I was far too scared to touch. Let's take a visit.
Kathy, what's the significance behind Maxwell's equations? Why are they important?
Oh gosh. Maxwell's equations are the foundation of physics. They relate all electrical and magnetic equations into 20 relations, which would then changed into 4 relations. And it changes everything from electricity being from electric charges and magnetic things into fields. Well, Maxwell called them fields. Faraday called them lines of force. And no physicist can call themselves a physicist without struggling through these equations.
Yeah, or engineer too. Electrical engineers have to go through it too.
Do they? Yeah, it's part of, and after Maxwell's equations, when people start believing in Maxwell's equations and they called themselves Maxwellians, it inspired all of modern physics.
Yeah.
After we looked at the books, we spent a little time in the museum, and then we went to lunch, and then we went to the Saturday electrical show. Towards the end of the show, both Jeffs and I were invited up for the cage, but Jeff Parisi pretended to be nervous so that he could film us. I then accidentally totally upstaged Jeff Bahari and was punished by Jeff's video being super blurry. After the talk, I learned that anyone over 18 years old could do the cage for like $10, which is how I got a nice video of the cage from the outside. When the huge Tesla coil was operating, you could sort of feel the electricity in the air, so to speak. It wasn't a violent thing, more of a subtle effect. Like in a storm where you feel like the hairs on your arms going up. The weird thing is the second you get in the cage, you can feel that the electricity in air is gone. I was told to touch the side of the cage, but I could tell that unlike a plasma ball, the electricity didn't see me. I've done many physics videos where I had to just trust that the physics would work. In this one, I could feel the physics working. Here's my video of the event. We believe in science. And Faraday. Oi.
Are you ready to get?
Yeah.
Yeah. Oh, you guys out of the gate,
So that was my reaction to the Spark Museum. I've realized in all of my videos, and this is my 85th video, I've never made one on the history and physics of the Faraday cage. So that is next time on the Lightning Tamers. So that's why I started to study the history and physics of the Faraday cage. And that is how I discovered that in 1837, Michael Faraday created the idea of electric fields and the concept of a dielectric because of his creation of the Faraday cage. Not only that, but by delving into Faraday's 1837 work, I started to feel that I truly understood Gauss's law for the first time. That is why I decided to take the plunge into understanding Maxwell's derivation of his laws, one equation at a time. It turned out to be the perfect method for me. Although I thought I would make a video about each equation, it turned out that one was enough to crack the whole can of worms wide open. Finally, I felt able to tackle the math Maxwell used, called quaternions, and study how it was transformed through Maxwell's equations into vector calculus. Then, as I understood Maxwell's odd language and quirks, I could also decipher not only Maxwell, but other early physicists' electricity and magnetism papers, like Hertz, Heaviside, Lorentz, Minkowski, Einstein, and of course, Poynting. However, when I went back to Feynman's lectures, I still couldn't figure out why it was so strange. It just made no sense. Then it finally hit me. Feynman's lectures, to put a fine point on it, are absolute gibberish. I know what you've been told. I have been told the same thing, but we were misinformed. I mean, just compare how Sommerfeld, who recall was the first major physicist to declare that B, not H, was the main magnetic field, made his argument in 1948, compared to Feynman's weak declaration of the same point 15 years later. Sommerfeld gave a list of arguments and included that he was contradicting his friend Max Planck's published opinion, and started an international debate on the subject. Then Feynman just pretends the debate over the magnetic field didn't even occur, aside from some nameless people who, as he mentioned as an aside in chapter 36, were confused by some simple math to think that H was the magnetic field. By the way, here's a little list of a few people who thought that H was the main magnetic field. John Henry Poynting, Heinrich Hertz, Oliver Heaviside, Hendrik Lorentz, Hermann Minkowski, Max Planck, Niels Bohr, and of course that simple-minded nobody, Albert Einstein. In addition, Feynman only introduced the H field and the permeability of a vacuum mu naught in chapter 36 as a convenient math shorthand to explain ferromagnetic or highly magnetic materials. And then he argues against the use of the permeability in a vacuum mu naught as just one more constant to keep track of. Otherwise, he replaced every instance of H with epsilon naught c squared b and every instance of D with epsilon naught e, even though that is only true in a vacuum with a constant magnetic field and is more complicated. That is how Feynman changed the Poynting vector to such a strange form, which isn't that upsetting to me because I believe it is a weak model. And also how he changed Gauss's law, Ampere's law, energy density, and in an act of pure insanity, Feynman just drops the equation for the velocity of an electromagnetic wave in a medium, v equals 1 over the square root of epsilon mu. It is just gone, kaput, vanished. Yes, you heard that right. Feynman just completely ignores Maxwell's equation that demonstrates the relation between electromagnetic light and the electric and magnetic properties of the medium. But how did Feynman justify changing what are considered some of the most fundamental equations in physics in his textbook? He didn't give any explanation. He just stated it like it was a fact. Well, that's not completely true. He did mention a bit about changing the equations in the introduction to his textbook. That's where he outright denied he made any changes, writing, quote, "In the first part of the course, dealing with electricity and magnetism, I couldn't think of any really unique or different ways of doing it, of any way that would be particularly more exciting than the usual way of presenting it. So I don't think I did very much in the lectures on electricity and magnetism." Just for comparison, here's how Sommerfeld represented Maxwell's laws in 1948. This is how a very popular physics book from Blaney and Blaney represented Maxwell's laws in 1957. And this is how Feynman presented them in 1963. Note that Faraday's laws of induction and Gauss's law for a magnet, the ones with B's and E's, are exactly the same in all three cases, but the other laws are completely different for Feynman. Just take a moment to compare and contrast. It is astonishing, isn't it? Even worse, Feynman created a new and terrible way of teaching physics. Feynman said that his method of teaching is
completely against history, and it's often complained about physics course there should be in terms of the experiments by which the information was obtained.
His reason for stripping physics of its motivation was,
It's necessary to learn all this physics in a limited time. I'm sorry, but we have to lose something. And one thing that we have a tendency to lose in these lectures is the historical experimental development.
no, Feynman, the historical approach isn't wasteful. It is fundamental. It is transformational. It is physics. And then there's how Richard Feynman evaluated his own lectures. He thought it was a disaster. No, really. Feynman wrote that the way the course was given, there wasn't any feedback from the students to the lecturer to indicate how well the lectures were going over. This is indeed a very serious difficulty, and I don't know how good the lectures really are. The whole thing was essentially an experiment. The question, of course, is how well this experiment has succeeded. My own point of view is pessimistic. I don't think I did very well by the students. I think the system is a failure. On that point, I agree. I completely agree. Now, I'm sure you have a lot of questions, and I would ask that you would please, for the love of Faraday, please ask someone else. Reddit has a lovely physics channel. Follow their rules, please. Their websites and Discord servers and tons of online geek hangouts stocked full of people just dying to debate physics. You'll be amazed, and keep bugging them until your questions are answered. If you subscribe to a YouTube science channel or personally know a physicist or advanced engineer, ask them what they think. I want this to be peer-reviewed beyond the level that any scientific idea has ever been peer-reviewed. I have a link to my script with lots of footnotes so you can cut and paste and ask specific questions. Like, is it true that Feynman changed most of Maxwell's equations and then pretended he didn't? Or is it true that D equals epsilon E only works for a dielectric in a constant magnetic field, and E equals negative del phi minus dA dt is the universal equation for the electric field? Or whatever you want to know or want to have clarified. Nothing would help me more than you questioning people's assumptions. Also, if you want to use any of this information or the information on any of my videos to help you create a podcast, a Wikipedia update, and please update Wikipedia. Wikipedia rocks. An article, a video, or a peer-reviewed paper, please do. Include the links for just such a reason. As long as you don't plagiarize me and believe in what you're saying, don't worry about using my ideas in research. In fact, I want you to use my ideas in research. I mean, I would like credit in places where it's appropriate, but that isn't my primary motivation. I literally just want to fight ignorance, cruelty, and elitism and have fun doing it. What could top that? Finally, to my science devotees throughout the world, those of you who love physics and engineering as much as I do, aren't you sick and dismayed with the terrible rise of cruel pseudoscience, fear of science, and outright anti-science belief? Aren't you done with wringing your hands with the ignorance in the world? Don't you want to show that physics isn't illogical, elitist, and
Cruel, screwy, intuitively screwy?
well, now is your time to shine. Print out the script, read every citation, get together with your smartest and weirdest friends, and stay up all night dissecting my ideas to the bone. And once you've made up your mind, whether you agree with me or not, put it out there in the world. Don't be scared of change. As the mighty Faraday said in his 7th research in electricity, which remember was the inspiration for Maxwell's equations, it is the great beauty of our science, that advancement in it, whether in a degree great or small, instead of exhausting the subject of research, open the doors to further and more abundant knowledge, overflowing with beauty and utility. For example, If you use the universal electric field equation, not only do you dispel the need for the crazy Poynting vector, but you also get a new equation for light. Rather than separate equations for the electric field, del squared E equals mu epsilon times the second time derivative of E, and a similar equation for the magnetic field, you get one intertwined electromagnetic equation, minus the gradient of the divergence of E, minus del squared K, equals mu epsilon times the second time derivative of E plus K, where K is just the time derivative of the magnetic momentum A, which is why I'm calling it the magnetic impulse. Now tell me, do you agree? Do you disagree? Can you model this with computers? Can you derive new equations from this? Let's do some physics, baby. This is going to be so much fun. Obviously, I am incredibly busy. However, I want to get the physics word out. So, if you want to arrange a film colloquia at your university, contact me and let's set something up. In addition, I don't want to ignore the artists, comedians, and artistic engineers. I love talking to artists. You are also beautifully inquisitive. Honestly, I need you. We need to convince everyone, physicists and non-physicists alike, that physics can be kind and welcoming. Because we have seen what happens when you let cruel Nobel Prize winners take over. Note that I absolutely hate elitist snobs. They are insufferable. I have no interest in how smart you are, how much you know about any subject, or how much money you have. Richard Feynman was very smart. Philip Leonard, an actual Nazi, was even smarter and a far better textbook writer. Instead, I care if you are kind, if you are creative, if you are generous, if you are inquisitive, if you are equally as interested in learning from people as you are at sharing your passions with them. I mean, if, as Voltaire said, anyone who can make you believe absurdities can make you commit atrocities, then isn't the opposite true as well? Anyone who can help you light the spark of knowledge can help illuminate the goodness in your heart. So that is my video. I'm sorry about being so bad at communication. This is especially true for my long-suffering patrons. Thank you, patrons. Remember, as Jonathan Larson so eloquently wrote, describing the joys of the artistic or the bohemian life.
The opposite of war isn't peace, it's creation.
So get cracking! And as always, stay safe and curious, my friends.